Welcome to our EE392 project based on marine mammals acoustic signal, based off using the concept of digital signal processing. To start off, the project has three important objectives to complete. The first objective is to visualize the raw data given the dataset and try removing the noise using the DSP toolbox in MATLAB. So looking at the first step, we have our input signal, our sampling frequency, and our audio read function of the first wave. And on the left hand side, we have all our data set. So for this example, we'll be using the first audio file. So the input signal is read. This is the length of the audio file and the vector. So to smooth the data, we will use a smooth function in MATLAB. And once we run this program in figure 2, we will get our smooth data graph as seen when we run it. This is figure 2, the smooth data of the input signal. So carrying on to the third graph, we will plot our signal waveform. So we will take the vector, the input signal, and get our signal waveform of the audio file, which is in figure 3. So this is the signal in time domain, amplitude against time. So you can see the frequency of the audio file. It has a little bit of noise. So in our next step, we will try to remove this noise by using Butterworth low pass filter. Butterworth filter is then implemented. This is applied simply to have a flat frequency response as possible. A low pass filter is implemented at this phase, and this is done because the audio signal, because low pass is used to lower the frequency at a certain cutoff. So in figure 4, we will get our low pass filter, as you can see. So moving on, now we will conduct spectral analysis. Spectral analysis, to be put in short term, is the filtered signals heat map. In this heat map, we will be able to see the frequency, the main frequency of the length of the audio file chosen. So to plot this signal spectrogram, we took the input signal. This is the length of our audio file. This is not the entire length of the audio file, since our audio file was around 5 minutes long. So we had to quarter that signal, because inputting the entire length of the audio file, it drew too much processing power for the MATLAB to run, and it would crash sometimes. So in order to limit this, we segmented this data. So we will be using quarter of the original signal. So in the quarter of the signal, we will half it to make it a little bit smaller. So the audio file will be around 30 seconds. So we will get a bit a filtered nice frequency. So we will plot the signal, and then we will get our heat map of our that is figure 6. Figure 6 is our amplitude of the spectrum of the signal, magnitude against frequency, as you can see. And our heat map is on here. This is the spectrogram of the signal, frequency and time. As you can see, the important signals are highlighted in yellow, meaning that this is our filtered signal and showing us the frequency of the mammals we want to detect. So objective 2 was to identify the marine mammals acoustic signal And some of the marine mammals we discovered were dolphins, which had 3 to 150 kilohertz frequency, snapping shrimp, which was 3.5 to 5 kilohertz, and the other was whale, which is 10 to 39 hertz. Whale 10 to 39 hertz is too big. As you can see, it just goes up to 150 kilohertz. So whale was exempted from this audio file. So we will just be looking at dolphin and shrimp. So for our third objective, we will identify the frequency of the mammals we know and compare it to the spectrogram of the signal and see if we do get a mammal in the audio file. So as you can see, the first signal goes till 150 kilohertz, proving that a dolphin's frequency range is within this audio. So next we will try to search for shrimp. A shrimp has 3.5 to 5 kilohertz. So you can see a bit of frequency, small frequencies here, here, here. Unfortunately, we could not come up with a program that would mark important signals on the map and had to manually see which frequency belonged to which mammal. So in our final part, we in addition to the three objectives, we also use windowing, Blackman and Henning window. This window function is used to just show a simple waveform to deliver non-zero values. So this is a visualization of Henning window. As you can see, this is the time domain and the frequency domain, and the other is a Blackman figure. Same time domain and frequency domain. This is usually the time domain, and this is we call the Fourier transform. As you can know, spectrogram already has a Fourier transform, STFT, short time Fourier transform. So this is the two graphs we get from Henning and Blackman. The length of this audio, this is the original size of the audio. We did not have to half or quarter it at this moment, because windowing and Henning methods, we were able to use the entire audio file without the MATLAB crashing or utilizing its entire processing power. So that is our project on marine mammals acoustic signals.